Hold up your hand and feel its weight. Almost all of that weight lives in the protons packed into every atom of you, and almost none of it comes from the things a proton is made of. The bulk of a proton's mass is energy, the energy of a force held in place that we have learned to read as weight. If you like following one idea all the way down, take a moment to subscribe and we'll keep going. For a long time, the proton looked like a tiny solid ball, the smallest brick of ordinary matter. Then physicists found a way to look inside, and the ball came apart into something stranger and far more alive. What we're chasing is the proton's hidden interior, and the question underneath it is simple. What is a proton actually made of? We'll build the answer slowly, one plain step at a time, starting from the outside and working in. Pour a glass of water and look at it. It seems still and plain, but it is built from pieces almost too small to imagine. A single drop holds something close to 1 trillion molecules of water, and every one of those is 2 atoms of hydrogen bound to 1 atom of oxygen. Hydrogen is the lightest thing there is, the first entry on the list of the elements, and at its heart sits a single proton. That one proton is the whole reason hydrogen is hydrogen. Take it away, and the atom is gone. So you are already holding protons every time you take a drink, by the countless billion. They are in the water, in the air you breathe, in your bones, in the chair beneath you. The proton is one of the most common objects in the entire universe, and for almost all of human history nobody knew it was there at all. When people first pictured the proton, they pictured a ball, a tiny, hard, solid ball, far too small to see, but a ball all the same, smooth on the outside and the same all the way through, like a marble shrunk down past the edge of sight. It carried a positive electric charge. It had a definite weight, and it sat quietly at the centre of the atom while the much lighter electrons moved around it. That picture is clean and easy to hold, and it served physics well for a long time. It is also wrong, in a way that took decades and some of the most ingenious experiments ever built to uncover. The proton is not a smooth ball. It is not solid, and it is not the same throughout. Look closely enough, and the simple marble comes apart into something restless and crowded, a small storm of pieces bound together by a force so strong that the pieces can never be pulled free. For now, hold the marble in your mind, because it is where everyone began, and it is worth honouring before we set it gently aside. Picture it about 1/10,000,000,000th of a centimetre across. That number means nothing on its own, so try it this way. Imagine you could blow up a single proton until it was the size of a pea. On that same scale, the atom around it would be a sphere larger than a football stadium, almost entirely empty, with the proton sitting alone at the very centre. Matter, for all its apparent solidity, is mostly nothing, with these tiny dense knots buried in the emptiness. And the proton is heavy for its size. It carries nearly all the weight of the hydrogen atom, roughly 2,000 times the weight of the lone electron circling it. When you feel the heft of anything at all, a stone, a cup, your own arm lifting from the table, you're feeling protons and their close cousins, the neutrons, doing almost all of the work. The electrons add hardly anything to the scale, so here is the simple, honest starting point. Ordinary matter is made of atoms. Atoms have a tiny, heavy centre. That centre is built from protons and neutrons, and the proton, the lightest nucleus there is, that single positive speck at the heart of hydrogen, is the thing we're going to take apart. We will do it the way the physicists did, slowly and in order, because the answer only makes sense if you climb to it one step at a time. We will start with how the proton first got its name. Then we will watch it look more and more fundamental, the final brick of matter, right up until the moment that picture cracked open. The marble is the door. On the other side of it is a place far stranger than any marble, and far more alive than anyone first guessed. The proton got its name from a man who began life on a farm. Ernest Rutherford grew up in New Zealand, one of 12 children, digging potatoes and helping his father, and he carried a plain, practical way of thinking into everything he later did. He liked to take a thing apart and find out what it was. Atoms were no different. Around the year 1909, in a laboratory in Manchester, England, Rutherford set his assistants a quiet experiment. They fired tiny positive particles called alpha particles at a sheet of gold foil so thin it was nearly see-through. The thinking at the time was that an atom was a soft, spread-out blob of positive charge with electrons scattered through it, like raisins in a pudding. Fire something at a pudding and it should pass straight through, barely nudged. Most of the alpha particles did exactly that. But once in a long while, about one in every several thousand, a particle came bouncing almost straight back, as if it had struck something hard and small. Rutherford later said it was the most incredible thing that ever happened to him, as if you had fired a heavy shell at a sheet of tissue paper and watched it rebound and hit you. There was only one way to make sense of it. The positive charge of the atom was not spread out at all. It was packed into a tiny, dense centre, with the electrons far outside it. Rutherford had found the nucleus. The atom was mostly empty, with a hard speck at its heart, and that speck held nearly all the mass. Then Rutherford kept going. A few years later, he fired alpha particles into nitrogen gas, and noticed that hydrogen nuclei came flying out. The alpha particles were knocking pieces loose from the nitrogen, and those pieces were the nuclei of hydrogen, the lightest and simplest of all. He had chipped a single positive unit out of a heavier atom. That told him something deep. The hydrogen nucleus was not just one nucleus among many. It looked like a basic building block, a piece that other nuclei were made of. So in the early 1920s, Rutherford gave it a name. He took the Greek word for first, protos, and called it the proton, the first one, the fundamental positive piece of matter. The name carried a claim inside it, the claim that this was a starting point, an original brick from which the heavier nuclei were assembled. For a while, the picture stayed almost too simple. People imagined that every nucleus was just a tight cluster of protons, with some electrons mixed in to cancel part of the charge. That idea ran into trouble, and it took the discovery of the neutron, the proton's neutral twin, by Rutherford's colleague James Chadwick in 1932 to set it right. After that, the nucleus made sense as a bundle of protons and neutrons packed together, the protons giving it charge and both giving it weight. But the proton itself stayed simple in everyone's mind. It was a point of positive charge with a mass and nothing more to say about it. You could measure its charge, you could measure its weight, and that seemed to be the whole story. It was a thing, not a place. It had no inside worth talking about. That is where the proton sat for the next few decades, named and weighed and trusted, treated as one of the smallest, simplest objects in nature. Rutherford had pulled it out of the atom and given it a name that means first. Nobody yet suspected that this first brick had a rich and crowded world hidden inside it, waiting for someone to look in the same hard, bouncing way Rutherford himself had looked into the atom. For a long stretch of the early 20th century, the proton looked like the bottom of things. You had 3 particles to build the world from, and the list felt satisfyingly short. There was the electron, light and negative, found by Joseph John Thomson in 1897. There was the proton, heavy and positive, sitting in the nucleus. And there was the neutron, heavy and neutral, found by James Chadwick in 1932. 3 pieces. From those 3 you could build every atom on the periodic table. It was a beautiful kind of simplicity, and it is worth pausing on, because simplicity like that is exactly what physicists hope for. You take the bewildering variety of the world, all the metals and gases and living things, and you find that underneath it sits a tiny kit of parts. Vary how many protons a nucleus holds, and you walk down the periodic table from hydrogen to helium to carbon to gold. Add electrons to balance the charge, and the atoms link up into molecules, and the molecules into everything else. 3 particles, arranged in different numbers. That was the whole recipe. In that picture, the proton was as fundamental as anything could be. It was a point, with a charge of exactly 1 positive unit, and a mass it never changed. It did not break. It did not decay. Left alone, A proton seemed to last forever, and nobody had ever seen one come apart or be built from anything smaller. When something refuses to break and refuses to change, it is natural to call it elementary, a true bottom piece with nothing underneath. There were good, hard numbers behind the confidence. The proton's charge was measured and found to be exactly equal and opposite to the electron's, to remarkable precision. That exact match was itself a kind of mystery, because the proton was so much heavier, yet the two charges balance perfectly, which is why atoms come out neutral and the world does not crackle with electric force. The proton's mass was pinned down too. It came out about 1,836 times the mass of the electron, a fixed number you could rely on. So through the 1930s and into the 40s, the proton kept it standing as a settled thing. The exciting questions seemed to lie elsewhere, in how the nucleus held together, in the new field of quantum mechanics, in the strange behaviour of electrons. The proton was a known quantity, a fixed point you could build on. You did not poke at the foundation, you stood on it. And there was a force holding the nucleus together that nobody fully understood, a force far stronger than our electricity, since something had to overpower the fierce repulsion of all those positive protons crammed into a space smaller than a millionth of a centimetre. They should have flown apart. They did not. Whatever glued them was powerful and short-ranged, and it was given a plain name, the strong force, long before anyone knew what it really was. That name will matter later, because the strong force turns out to be the secret of the whole story. But in those years the proton was just a brick, and a brick has no inside. The question, what is a proton made of, would have sounded almost meaningless, like asking what a single point is made of. It was the answer, not the question. It was where the chain of what is that made of finally stopped. That calm did not last. The trouble did not come from looking inside the proton. It came from the sky and from new machines, which began producing particles nobody had ordered and nobody could fit into a list of 3. The kit was about to overflow. The trouble started with cosmic rays and then with the first big accelerators, and it arrived as a flood. Through the late 1940s and into the 50s, physicists kept finding new particles. Not 1 or 2, dozens. And every one of them was heavy, like the proton, and felt the strong force, like the proton, and yet none of them fit the tidy list of 3. They came first from the sky. High in the atmosphere, particles from deep space slam into the air and break apart, raining fragments down through the clouds. Physicists hauled photographic plates up mountains and flew them on balloons to catch the tracks, and in those tracks they saw things they could not name. Then the accelerators arrived, machines that smashed protons together hard enough to make new matter out of the energy of the collision, and the flood became a deluge. There were particles called pions and kaons, lighter than the proton but new all the same. There were heavier ones, the lambda and the sigma and the zacc, that behaved almost like overweight cousins of the proton. There were short-lived states called resonances that appeared for the briefest flicker and then fell apart. By the end of the 1950s, the count of these strongly interacting particles had climbed past 100, and it kept climbing. The physicist Willis Lamb joked when he accepted a major prize that the discoverer of a new particle used to be rewarded, but now ought to be fined. Another, looking at the mess, said that if he had wanted to memorize the names of so many particles, he would have become a botanist. They called the whole sprawling collection the particle zoo, and the joke had teeth, because a zoo is exactly what it felt like. Cage after cage of strange animals, each carefully described and labelled, with no family tree to tie them together. This was a real crisis, and it is worth feeling the weight of it. The proton had been a foundation precisely because it was simple and rare in kind. Now it was one face in a crowd. If the proton was elementary, then so were 100 other particles, and 100 elementary building blocks is not a foundation. It is a failure. The whole appeal of the 3-particle picture had been that a short list explained a long one. A list of 100 explains nothing. It just pushes the bewilderment of the world down one level and leaves it there. So the zoo became a question that demanded an answer. Surely all these particles were not separate and unrelated. Surely there was a pattern hidden in them, the way the periodic table had hidden a pattern in the elements, waiting for someone to spot the order. The chemists had once faced a similar mess, 60-odd elements with no clear scheme, until Dmitri Mendeleev laid them out in a grid, and the gaps in his grid predicted elements no one had yet found. The particle physicists were waiting for their own Mendeleev. The hope was simple to state. Maybe these hundred-some particles were not fundamental at all. Maybe they were made of a much smaller number of pieces combined in different ways, the way a handful of letters spells thousands of words. If you could find those few pieces, the zoo would collapse back into something a person could hold in their head, and the crowd would turn out to be patterns built from a quiet alphabet. That hope had a serious cost, though, and everyone could see it. If the heavy particles were made of smaller pieces, then the proton was made of smaller pieces too. The foundation would crack. The first brick would turn out not to be a brick. To save simplicity, physics would have to give up the idea that the proton was the bottom. Someone had to be willing to look underneath it. The man who first laid out the order was Murray Gell-Mann, and he was the kind of mind that collected things. He spoke many languages, knew the proper pronunciation of every name, watched birds, and could not resist a clever word. He was brilliant and a little impossible, and he had spent years staring at the particle zoo looking for its hidden grid. In the early 1960s he found one. He arranged the heavy particles into neat geometric patterns, groups of 8 and 10, and the patterns were so clean that they predicted a missing particle, the omega minus, which was then found just where the pattern said it should be. A pattern that good is not a coincidence. It is a sign that something simpler lies underneath. By 1964, Gell-Mann had worked out what that something might be. If you suppose there were just 3 basic pieces, and you combined them in 2s and 3s, the whole zoo fell into place. The proton, the neutron, the pions, the kaons, the lambda, all of them came out as different arrangements of the same 3 pieces. 100 animals reduced to 3. Gell-Mann needed a name for them, and here his love of odd words took over. He had a sound in his head. Quirk, before he had a spelling. Then he came across a line in the novel Finnegan's Wake by James Joyce, a strange, dreamlike book full of invented words, and the line read 3 quarks for muster mark. 3 quarks. It fit perfectly since he needed 3 of them, and it had no ordinary meaning to drag along. So the pieces became quarks, and physics kept the spelling and Gell-Mann's own pronunciation. At almost the same moment, working separately at the same laboratory in Geneva, a young physicist named George Zweig reached the very same idea. He had been thinking about the same patterns and came to the same conclusion, that the heavy particles were built from a few fundamental pieces. He called his pieces aces, after playing cards, and imagined 4 of them. The name aces did not stick, but the idea was the same, and the 2 of them, Gell-Mann and Zweig, are remembered together as the fathers of the quark model. Gell-Mann proposed 3 kinds of quark, 3 flavors as physicists came to say, though flavor here has nothing to do with taste and is just a label for a type. He named them up, down, and strange. Plain, almost silly words for the deepest pieces of matter. The proton, in this scheme, was made of 3 quarks, and so was the neutron, and the lighter particles like the pions were made of a quark paired with an antiquark, a quark's mirror image partner. It was a stunning simplification, and it should have been celebrated at once. It was not. The trouble lay in one strange feature of the quarks, a feature so odd that Gell-Mann himself was cautious about claiming the quarks were real. For the arithmetic to work, the quarks could not carry whole units of electric charge. They had to carry fractions, and a fraction of the basic charge was something no one had ever seen, and many physicists were sure no one ever would. So the quark began its life as a half-believed idea. It was a bookkeeping trick that made the zoo behave, an elegant pattern on paper, and possibly nothing more. Even its inventor sometimes spoke of quarks as a mathematical convenience rather than solid objects you could ever hope to hold. The proton might be 3 of these things, or the three things might be a useful fiction. To find out which, someone would have to either catch a quark in the open or look inside the proton hard enough to see them. The strange charge is what made the doubt, and it is the next thing to understand. To see why so many serious people doubted the quarks, you have to understand how solid the rule about electric charge had been. Charge came in whole units. The electron carried exactly one negative unit. The proton carried exactly one positive unit. Every charged particle anyone had ever measured carried a whole number of these units. 1, or 2, or 3, never a piece of 1. This was not a guess. It had been measured with great care, most famously by Robert Millikan in an experiment with tiny oil drops, and the charge always came out as a whole multiple of a single basic amount. Charge was lumpy, and the lumps were indivisible. The quark model broke that rule on purpose. For the proton to come out with its one full positive unit while being built from 3 pieces, the pieces had to carry fractions. The up quark was assigned 2/3 of a positive unit. The down quark was assigned 1/3 of a negative unit. Put 2 ups and 1 down together, and the fractions add up exactly. 2/3 plus 2/3 is 4/3, minus 1/3 leaves 1. 1 full positive unit. The proton's charge fell out of the arithmetic cleanly, but only by paying in thirds. To a physicist trained on whole charges, this was deeply unsettling. 1/3 of a charge had never been seen in any experiment, ever. It violated the most reliable pattern in all of particle physics, and so the natural response was to try to catch one. If quarks were real and lived inside every proton, then surely you could knock one loose. Break a proton hard enough, the thinking went, and a quark should come tumbling out, carrying its telltale fractional charge, easy to spot because it would behave like nothing else. People looked, and they looked hard for years. They searched in cosmic rays, sifting through the particles raining down from the sky. They searched in the debris of accelerator collisions. They searched in ordinary matter, in seawater and in moon rocks and in deep-sea sludge, on the reasoning that if a stray quark existed anywhere, it might have settled out over the ages. They even repeated Millikan's oil drop idea with more sensitive setups, hunting for any speck that carried 1/3 of a charge instead of a whole one. Nobody found a quark, not one, anywhere, ever. Every search came back empty. No fractional charge turned up loose in nature. No lone quark flew out of any collision, no matter how violent. And this absence was damning. If the proton was simply 3 little balls glued together, you ought to be able to pry one out, the way you can break a molecule into atoms or chip a proton out of a nucleus the way Rutherford had. The fact that no one ever succeeded looked, to many, like proof that quarks were just a fiction after all, a neat pattern on paper with no physical pieces behind it. This is the strange knot at the centre of the early quark story. The model worked beautifully. It organised the zoo, predicted new particles, and explained the charges of everything. Yet the things it was built from could not be found, no matter how anyone tried. Either the model was a clever illusion, or the quarks were real but bound so tightly that escape was simply impossible. A kind of imprisonment with no exception ever observed. For a few years, no one could say which it was. The doubt was honest and earned. The way out did not come from catching a quark in the open at all. It came from a different kind of looking, a way of seeing inside the proton without ever pulling its pieces free, by firing something small and fast straight into it and watching, very carefully, how it bounced. The machine that cracked the proton open sits in California, and it is 2 miles long. At the Stanford Linear Accelerator Center, built in the 1960s, electrons are driven down a straight tube that runs for about 3 kilometers under the hills, a little under 2 miles, the longest straight machine of its kind. Along that run, the electrons are pushed faster and faster until they are moving at very nearly the speed of light, carrying enormous energy in each tiny particle. Then they are aimed at a small target, a bit of liquid hydrogen, which is to say a target full of protons, and the physicists watch what happens when an electron meets a proton head-on. The electron is the perfect tool for the job. It feels electric charge but not the strong force, so it is not tangled up in whatever holds the proton together. It simply responds to the charge it meets. And the electron, as far as anyone can tell, is a true point, with no size and no inside of its own. So firing an electron at a proton is like probing an unknown object in the dark with the sharpest possible needle. The needle has no parts to confuse the picture. Whatever you learn comes from the thing you are poking, not from the poker. There is a deeper reason a fast electron makes a good probe, and it comes from quantum physics. A particle is also a wave, and the faster you make it, the shorter its wavelength becomes. A short wavelength is what lets you see small detail, the same way you cannot make out fine features with long, lazy ocean swells, but you can with short, tight ripples. To see inside something as small as a proton, you need a probe with a wavelength smaller than the proton itself. That means very high energy. The 2-mile machine existed precisely to push electrons to energies high enough that their wavelength shrank below the size of the proton, sharp enough to resolve whatever lay within. The experiment was led by 3 physicists, Jerome Friedman, Henry Kendall, and Richard Taylor, working through the late 1960s with a large team. The plan sounds simple: fire electrons at protons, measure where the electrons go afterward, at what angles and with how much energy left. From the pattern of the scattering, read off what the electron must have hit. The execution was anything but simple. It meant enormous detectors swinging on great steel arms to catch electrons coming off at many angles, and careful counting of rare events, the kind of patient, grinding work that real discovery is usually made of. The name for this kind of experiment is deep and elastic scattering, and the words are worth unpacking plainly. Deep means the electron strikes hard enough to reach inside the proton, rather than just glancing off the whole thing. Inelastic means the proton does not stay whole and bounce away unchanged. It gets shaken apart, its energy scattered into a spray of new particles, so that what comes out is not the tidy proton that went in. The electron, in effect, reaches in, strikes something within the proton, and the proton shatters into fragments while the electron flies off carrying the news of what it touched. The thinking before the experiment was that if the proton were a soft, evenly spread blob of charge, the electrons would mostly pass through with only small deflections, nudged gently the way the alpha particles had once been expected to drift through the pudding atom. A smooth, uniform proton would give a smooth, gentle pattern of scattering, with hard bounces almost never happening. The team set up to measure exactly that pattern, expecting it to be soft. What they actually saw was not soft at all. Now and then an electron came tearing back at a steep angle, having struck something small and hard deep inside the proton, and that bounce was about to change everything. The electrons that came back at wide, steep angles were the whole story, and the echo across the decades was almost exact. Most of the electrons fired into the proton behaved tamely, passing through with small deflections, just as a soft, spread-out charge would predict. But a stubborn fraction did something the smooth proton picture flatly forbade. They bounced hard, kicking back at large angles, carrying the unmistakable sign of having hit something tiny and solid inside. If you knew the history, the feeling was uncanny. This was Rutherford's gold foil all over again, one level deeper. Half a century earlier, alpha particles bouncing back from the atom had revealed a hard nucleus hidden in the empty pudding. Now electrons bouncing back from the proton revealed hard points hidden inside what everyone had treated as the final, indivisible brick. The same trick, the same surprise, the same lesson. When something small and fast rebounds sharply, it has struck something even smaller and harder, a concentrated lump rather than a soft smear. The proton was not a smooth blob of charge. It had grit inside it, point-like pieces that the electrons could ricochet off, one at a time. The numbers carried the message even when intuition wanted to resist it. A soft proton and a grainy proton predict very different patterns of how often electrons scatter at each angle, and the measured pattern matched the grainy one. The rate of hard, wide-angle bounces was far higher than any smooth distribution of charge could produce. Something inside the proton was concentrated into points, and the electrons were occasionally hitting those points squarely, the way a thrown pebble will sometimes strike a single hard seed inside a soft fruit and snap back. It is worth sitting with how strange this was for the people who saw it. They had set out expecting the proton to behave as one soft object. Instead, the data said the proton was a container, and the electron was not bouncing off the proton as a whole, but off separate hard things within it. The proton had an inside, and that inside had structure, and the structure was lumpy. The marble had grit in it. The final brick was not final, and the thing physics had stood on for decades had a flaw of its own that gave way under a hard enough knock. The discovery was solid enough to earn its makers the highest recognition. Jerome Friedman, Henry Kendall, and Richard Taylor shared the Nobel Prize in Physics in 1990 for these experiments, the prize naming the deep inelastic scattering of electrons that revealed the proton's inner structure. It was the experimental ground that turned the quark from a paper convenience into something with a real claim on the world. You could not hold the pieces, but you could feel them, the way you can feel pebbles inside a sealed bag by how it resists your hand. And yet a careful person had to stay honest about what the experiment showed and what it did not. The bounces proved that the proton contained small, hard, point-like things. They did not, on their own, prove that those things were Gell-Mann's quarks. The experiment saw points. It did not come stamped with the name of the points or their fractional charges. A real gap remained between the raw result, which was hard scattering off little points inside the proton, and the bold claim, which was that those points were the up and down quarks with their strange thirds of charge. Closing that gap was the next task, and it fell to a way of thinking that treated the proton as a loose bag of nearly free pieces during the brief, violent instant of the collision. The man who framed it gave the points a working name of their own, before anyone was sure they were quarks, and that frame is what finally tied the bounce to the theory. The man who built the bridge was Richard Feynman, one of the most original physicists of the century, known for working everything out from scratch in his own pictures, rather than trusting someone else's equations. When he looked at the Stanford results, he did not start by assuming quarks. He started by asking a simpler question. What would the scattering look like if the proton were just a bag of small, independent pieces, whatever they were? He gave those pieces a deliberately plain name. He called them partons, from the word part, meaning simply the parts of the proton, with no commitment to what they were made of or what charge they carried. His insight rested on speed and time. When a very fast electron strikes the proton, the collision is over in an unimaginably brief instant, far shorter than the time it would take the pieces inside to shift around or talk to one another. In that frozen moment, each parton acts as if it were alone and free, not bound to its neighbours at all, so the electron does not scatter off the whole proton, and it does not scatter off some smeared average. It strikes a single parton, one piece, while the others stand still around it. The hard bounce is the electron hitting one free parton dead on. This picture made a sharp, testable prediction, and the prediction is what sealed it. The physicist James Bjorken had worked out from the underlying theory that if the proton were truly built of point-like pieces, the scattering pattern should show a particular kind of simplicity. As you fired electrons harder and harder, the results should stop depending on the energy in the way a soft object would demand, and instead settle into a fixed shape that depended only on the fraction of the proton's momentum carried by the piece that was struck. This behaviour is called Bjorken scaling, and its meaning is plain. The pattern stays the same as you probe harder, because there is no smaller scale to find, no soft size to the pieces, nothing but points. When the Stanford data were examined, they showed exactly that scaling. The pattern held its shape as the energy climbed, just as point-like pieces required, and just as a soft-sized object would have forbidden. Feynman's free partons and Bjorken's scaling fit the measurements together, and the fit was tight. The proton really did behave, in that frozen instant of collision, like a loose collection of independent points. Now the pieces of the argument could be laid side by side. The quark model, from Gell-Mann and Zweig, said the proton was made of 3 fundamental pieces with fractional charges. The Stanford experiment said the proton contained small, hard, point-like pieces. Feynman and Bjorken's Parton picture said those pieces should act free and give scaling, and they did. The natural reading, once the dust settled, was that the partons were the quarks. The points inside the proton were Gell-Mann's up and down quarks, finally seen, not by catching one in the open, but by watching electrons rebound off them one at a time. Even the fractional charges, the very feature that had drawn so much doubt, left their mark in the data, in just how strongly the electrons scattered. The strength of the bounce depends on the charge of the thing struck, and the measured strengths lined up with the odd thirds the quark model demanded rather than with whole units. The strange charges were not caught in a jar. They were read off the way the proton's interior pushed on a passing electron, so the half-believed bookkeeping trick had become a thing with parts you could probe. The proton was not the bottom. It was 3 quarks held inside, and the next task was to say plainly which 3. So now we can say what the proton is made of in the simplest first version of the answer. It holds 3 quarks. 2 of them are up quarks, and 1 is a down quark. That is the recipe, written down by Gell-Mann's model and confirmed by the bounces at Stanford. 2 up, 1 down. Say it a few times, because it is the line everyone learns first, and it is true as far as it goes, though it will turn out to be only the beginning of a much fuller story. Watch how cleanly the charges work, because this is where the strange fractions earn their keep. The up quark carries 2/3 of a positive unit of charge. The down quark carries 1/3 of a negative unit. Take 2 ups and 1 down and add them up. 2/3 plus 2/3 gives 4/3 of a positive unit. Then the down quark subtracts 1/3. 4/3 minus 1/3 leaves exactly 1. 1 full positive unit of charge, which is precisely the charge of the proton. The odd thirds, the very thing that made people doubt quarks for years, combine into the plain whole number we always measured from outside, and the same 3 pieces in a slightly different mix give you the neutron. Swap 1 up for 1 down, so you have 1 up quark and 2 down quarks. Now the charges read 2/3, minus 1/3, minus 1/3. 2/3 minus 2/3 leaves 0. The neutron comes out with no charge at all, which is exactly right, since the neutron is the proton's neutral twin. 2 of the most important particles in the universe, the 2 pieces of every atomic nucleus, are the same 3 quarks shuffled by a single swap. Proton, 2 up and 1 down. Neutron, 1 up and 2 down. That is the whole difference between them at this level. These 3 quarks have a special name worth knowing. They're called the valence quarks of the proton, borrowing a word from chemistry, where valence describes the outer electrons that set an atom's character. The valence quarks are the proton's defining quarks, the ones that fix its charge and its identity. When you ask what kind of particle this is, a proton or a neutron or something else, you're really asking which valence quarks it carries. They are the part of the answer that makes the proton a proton. It is tempting to stop here and feel that the question is settled. The proton is 2 up quarks and a down quark, the charges add to 1, and the matter seems closed. For a simple cartoon of the proton, 3 little balls in a bag, that picture is good enough, and it will get you through a great many conversations. But it hides 2 enormous puzzles, and the rest of this story is mostly about them. The first puzzle is escape. If the proton is just 3 quarks in a bag, why can no one ever pull one out? Every attempt to free a quark has failed, completely and without exception, and that is not the behaviour of 3 loose balls. The second puzzle is weight. The proton has a definite mass, the heft you feel in every object. But the 3 quarks, added up, account for almost none of it. The numbers do not even come close. Something other than the quarks is supplying nearly all the weight. Both puzzles point to the same hidden thing, the force that binds the quarks. We named it long ago the strong force, without understanding it. Now we have to look at it directly, because the proton is far less a bag of three balls than it is a knot of that force, and the force is where its deepest secrets live. We begin with why a quark will never come out. Here is the rule that no experiment has ever broken. You cannot pull a single quark out of a proton, not by hitting it harder, not by any trick yet tried. A quark always stays bound up with others, never alone, never naked in the open. Physicists call this confinement, and it is one of the strangest and most important facts about the strong force. Quarks are real, they're inside the proton, and they're also imprisoned there for good. To feel why, you have to set aside the way every other force behaves. Take gravity or electricity. Pull two magnets apart or lift a weight against gravity, and the force between them weakens as they separate. Get far enough away, and the pull fades to almost nothing. This is so familiar that it feels like a law of the world. Things let go of each other when they get far apart. The strong force does the opposite, and that single reversal is the heart of confinement. Picture two quarks joined by the strong force, and imagine the force as a band stretched between them, almost like a length of elastic. When the quarks sit close, the band is slack and the pull is gentle. Now try to drag them apart. As they separate, the band does not loosen, it tightens. The further you pull, the harder it pulls back, because the strong force between them does not fade with distance the way other forces do. It holds steady, even grows, so that separating two quarks takes more and more energy the further you go, with no relief and no end in sight. Stay with the elastic band, because its next move is the key. Keep stretching a real band and eventually it snaps. The strong band snaps too, but what happens at the break is the surprising part. You poured energy into stretching it, and that energy, by the deep rule that energy can become matter, turns into a brand new quark and antiquark right at the broken ends. So instead of a free quark coming loose, you have made a fresh pair. The quark you are dragging now has a new partner, and the place you dragged it from has one too. You pulled to get one quark alone and ended up with two bound pairs instead. This is why the searches in seawater and moon rocks and cosmic rays all came back empty. It was never a question of pulling harder. Pulling harder only feeds more energy into the band, and more energy makes more quarks, never a lone one. Nature has a firm rule that quarks travel only in groups that hide their fractional charges. 3 quarks together as in a proton, or a quark with an antiquark as in the lighter particles. A single quark with its naked third of a charge simply never appears, because the moment you try to make one, the strong force spends your effort building company for it instead. Notice how neatly this dissolves the old paradox. For years, the absence of free quarks looked like evidence against them. Now the same absence is exactly what the strong force predicts. Quarks are real and confined, both at once, and the two facts no longer fight each other. The proton can be made of quarks that no one can ever extract, and there is nothing contradictory about it. But naming confinement is not the same as explaining it. Why does the strong force behave so strangely, holding firm across distance when every other force fades? The answer needed a new idea, a new kind of charge that the quarks carry, different from electric charge and obeying its own deep rule. That new charge has a colour in its name, though it has nothing to do with light, and it is where we turn next. The strong force needed a charge of its own, and the charge that physicists found has a strange name. They called it colour. It has nothing to do with the colours you see, nothing to do with light or paint. It is simply a label, borrowed because the rules it follows happen to work like the mixing of colours, and the name stuck because it was easy to picture. Colour is to the strong force what electric charge is to electricity. It is the property that makes a quark feel the strong pull and the source of everything that holds the proton together. The reason physicists needed a new charge at all came from a problem with the quarks as first described. Some particles seem to be made of 2 or 3 identical quarks sitting in the same state, which a deep rule of quantum physics flatly forbids. 2 identical quarks cannot occupy the very same condition. Any more than two things can be in the same place in the same way. The way out was to suppose the quarks were not quite identical after all. Each carried a hidden extra label that made it distinct, and that label was colour. Colour comes in three kinds, and following the loose analogy with light, they were named red, green, and blue. A quark carries one of these three. This is not a thing you could ever see or photograph. It is a charge, a property like electric charge, but with three varieties instead of the simple plus and minus. And the deep rule of the strong force is a rule about colour. Quarks can only gather into groups whose colours balance out, groups that are, in the language of the analogy, colourless or white. Watch how the proton obeys this. It has three quarks, and they carry the three different colours, one red, one green, one blue. In the colour analogy, red and green and blue light together make white, and that is exactly the point. The three quarks of a proton carry the three colours that combine to colourless. The proton, as a whole, is colour neutral, balanced, white. That balance is not optional decoration, it is the rule that decides which combinations are allowed to exist. Three quarks of three different colours make a balanced, allowed particle, and that is precisely why the proton is built of three. The lighter particles obey the same rule a different way. A quark carrying a colour paired with an antiquark carrying the matching anticolour also balances to neutral, the way a colour and its opposite cancel. So nature allows two main kinds of stable grouping. Three quarks of three colours, which gives you protons and neutrons, or a quark and antiquark with cancelling colours, which gives you the lighter particles. Both come out colourless. A lone quark carrying a single uncancelled colour is not balanced, and so it is not allowed to stand alone. Here, in the rule of colour, is the deeper root of confinement we met before. This whole framework, the theory of colour charge, and the strong force built on it, was given a formal name in the 1970s. It is called quantum chromodynamics, and the long word breaks down simply. Quantum, because it follows the rules of the quantum world. Chromo, from the Greek for colour, because colour charge is at its heart. Dynamics, because it describes how things move and interact. Quantum chromodynamics, the dynamics of colour charge, usually shortened to its initials. It is the theory of the strong force, the rulebook of the proton's interior, and it stands today as one of the best tested theories in all of physics. But colour charge, like electric charge, needs something to carry the force between the quarks. Electricity has its carrier, the strong force has its own, and these carriers turn out to be as important to the proton as the quarks themselves, and far stranger in how they behave. Forces are carried. This is one of the quiet, deep ideas of modern physics, and it is worth holding plainly. When two electrons push apart, they are not reaching across empty space by magic. They are passing something back and forth, a particle of light called a photon, traded between them, and that trading is what we feel as the electric force. Every force works this way, through carrier particles passed between the things that feel it. The strong force is no exception, and its carriers have a name that fits their job. They are called gluons, because they are the glue. The gluons are what hold the quarks inside the proton. A quark emits a gluon, another quark absorbs it, and that constant exchange is the strong force in action, the pull that binds two up quarks and a down quark into a single proton. The gluon carries colour charge from one quark to another, shuffling the colours around while keeping the whole proton balanced. So the inside of a proton is not three quiet quarks sitting still. It is three quarks furiously trading gluons, a blizzard of exchange going on without pause, and that blizzard is the binding. Now comes the feature that makes the strong force unlike anything in ordinary experience, and it is the single most important difference between gluons and photons. The photon, the carrier of electricity, has no electric charge itself. Light does not push on light. Two beams cross without touching. The carrier of electricity is blind to the very force it carries. The gluon is not like that at all. The gluon carries colour charge, and because it carries colour, the gluon feels the strong force. Gluons pull on gluons. The glue is sticky to itself. This sounds like a small technical point, and it is anything but. Sit with what it means. The carriers of the strong force attract one another, so the force is not just acting between the quarks. It is acting within itself, gluons grabbing gluons, the binding feeding on its own carriers. Where the lines of electric force spread out and thin into space, growing weaker, the lines of the strong force are pulled together by the gluon's own stickiness, gathered into a tight, narrow tube running between the quarks. That gathering into a tube is the elastic band we imagined earlier, the band that does not weaken with distance. The gluons clinging to one another are why the band stays taut, why pulling quarks apart only costs more, why confinement holds. So the gluon explains the strange behaviour we have been circling. Because gluons interact with each other, the strong force refuses to fade with distance the way electricity does. The self-attraction of the carriers concentrates the force into a band of unbreakable pull. The same self-attraction makes the proton's interior a far busier place than the simple three-quark picture suggested. There are not only quarks in there. There is a thick churning field of gluons, the glue thrashing between the quarks and clinging to itself, and that field carries energy, a great deal of it, which will matter enormously when we ask about the proton's weight. How many kinds of gluon are there? Colour comes in 3, and gluons carry combinations of a colour and an anti-colour, which works out to 8 distinct gluons in all, 8 varieties of glue trading through the proton. The exact count comes from the deep structure of the theory, and the plain takeaway is that the proton's binding is not one simple thread, but a rich, 8-fold web of self-clinging carriers. The gluon's habit of sticking to themselves has one more consequence, the most surprising of all. It means the strong force changes its strength depending on how close the quarks are, and it changes in a direction that runs exactly backward from common sense. That reversal won a Nobel Prize, and it is where we go next. The strangest fact about the strong force is that it runs backward from every instinct you have. Think again about how forces usually behave. The closer two things are, the harder they pull or push. Bring 2 magnets together and the tug grows fierce. Move them apart and it eases. Strength rises as distance shrinks. This is so deeply familiar that it feels like it could not be otherwise. The strong force between quarks does the reverse, and the reversal is so important it has its own name. When 2 quarks are very close together, almost on top of each other, the strong force between them is weak, astonishingly weak. In that tight embrace, the quarks barely feel the binding, and they move almost as if they were free, drifting nearly untouched by the force that is supposed to chain them. Then, as you draw them apart, the force grows. Farther apart, stronger pull, until at the distances across a whole proton the binding is fierce and unbreakable. The strong force is feeble up close and mighty at range, the exact opposite of electricity and gravity. This is the deep reason behind both mysteries we met earlier, and it ties them into one. It explains the Stanford bounces, where the electron struck a quark in that brief instant, and the quark behaved as if free, because at the tiny distance of a hard collision the strong force had nearly let go. And it explains confinement, because trying to pull a quark out means crossing to large distances, where the force only grows, the band only tightens, and escape only gets harder. Weak when near, strong when far. One rule. Both puzzles. The property has a name that captures the surprise. It is called asymptotic freedom, and the phrase, once unpacked, says it plainly. Freedom, because the quarks move freely when packed close. Asymptotic, a mathematician's word meaning as you approach a limit, here the limit of zero distance, where the force fades toward nothing, and the freedom becomes nearly complete. As the quarks approach each other, they approach freedom. Pull them apart and the cage closes. The discovery was a feat of pure calculation, worked out on paper in 1973, before the full theory was even accepted. 3 physicists found it. David Gross and his graduate student Frank Wilczek, working together at Princeton, and independently David Politzer, then a graduate student at Harvard. They were doing hard mathematics on how the strong force changes with distance, and the answer that came out ran against every expectation. Gross, by his own later account, had set out half expecting to prove that no sensible theory could behave this way, and instead found that this one did. The mathematics insisted that the force weakened up close, and the surprise was genuine even to the people deriving it. The result was momentous because it rescued the whole picture. Asymptotic freedom is what allowed quantum chromodynamics, the theory of color charge, to make sharp predictions and match the Stanford data, where quarks acted free inside the proton. It explained why the Proton picture worked at all. It turned the strong force from a vague idea into a precise, calculable theory. For this, Gross, Wilczek, and Politzer shared the Nobel Prize in Physics in 2004, the prize naming their discovery of how the strong force behaves at short range. And it deepens the portrait of the proton in a way we're now ready to follow. Inside the proton, the quarks are close enough that they move almost freely, yet the binding still rules at the proton's edge and keeps them locked in. The space they move in is not empty. It is filled with the churning gluon field, and that field is restless enough to do something we have not yet counted. It can conjure quarks out of energy itself, filling the proton with far more than the three we started with. Up to now we have spoken of the proton as three quarks, the two ups and the down, with gluons binding them. That picture is too quiet. The real inside of a proton is not three steady quarks in a calm room. It is a boiling, crowded place, and most of what fills it was never on our list. To see why, we have to take seriously something the quantum world allows that ordinary intuition does not. Empty space is not truly empty, and the inside of a proton least of all. The rule behind this is one of the deep oddities of quantum physics. Energy can flicker into being for a brief instant, borrowed from nothing, as long as it is paid back quickly enough. In that fleeting moment, the borrowed energy can take the form of matter, a particle and its antiparticle appearing together, existing for a flash, then meeting and vanishing again. This is not a fantasy or a figure of speech. These flickering pairs leave measurable fingerprints, and physics counts on them. They are called virtual particles, virtual because they live only in the borrowed instant, never settling into permanent existence. Inside the proton, the gluon field is so thick and so energetic that this flickering becomes a constant storm. Gluons split into quark and antiquark pairs for an instant, and those pairs fold back into gluons over and over everywhere without pause. A down quark and its antimatter twin wink into being and wink out. An up pair appears and is gone. Even heavier kinds of quark flicker up briefly when the energy allows. The proton is not three quarks in empty space. It is three quarks swimming in a churning broth of gluons and short-lived quark-antiquark pairs, a place that never holds still. Physicists have a name for this churning crowd. They call it the sea. The two up quarks and the one down quark are the valence quarks, the permanent residents that fix the proton's identity. Around them, filling the space, is the sea of virtual quarks and antiquarks and gluons, flickering in and out, a restless population with no fixed members, only a constant turnover. The valence quarks set what the proton is. The sea is the living medium they swim in. The sea is not a minor footnote to the proton. It is most of what is there by many measures. If you probe the proton hard enough, you find far more going on than three quarks would ever produce. You find antiquarks, which a simple three-quark proton should not contain at all, yet there they are, members of the sea. You find that at any instant the proton holds a shifting number of pieces, not a tidy three, and the harder you look, the more you see, because a sharper probe catches more of the brief flickers. The proton's contents depend on how closely you examine it, and that strange feature traces directly back to the boiling sea. So the honest answer to what a proton is made of has grown stranger than the clean line about two ups and a down. Yes, it has those three valence quarks, the ones that give it its charge and its name. But it is also full of gluons binding everything together, and full of a sea of quark-antiquark pairs flickering up from the energy of the strong field and falling back. It is less a small bag holding 3 marbles than a tiny ferocious storm, a knot of force so energetic that it is forever spinning matter into being and letting it dissolve. That storm is about to answer the question of weight, the one that has been waiting since the start. The 3 quarks barely weigh anything, yet the proton is heavy. The mass has to come from somewhere, and now, with the sea and the gluon field in view, we can finally see where it lives. We come now to the strangest fact in this whole story, the one promised in the first minute. The proton has weight, real heft, the kind you feel in any object you lift. And the things it is made of, the quarks, supply almost none of that weight. The numbers are not merely off by a little. They miss by so much that the simple idea that the proton weighs what its parts weigh collapses entirely. Nearly all the mass of the proton comes from somewhere other than its quarks. Lay out the numbers and the gap is stark. The proton has a certain mass, the standard against which we measure the small particles. The up quark on its own weighs only about 2 units on the scale where the proton weighs around 938. The down quark weighs only about 5 such units. Add up the proton's 3 valence quarks, 2 ups and a down, and you get something near 9 units. 9 out of 938. The quarks account for roughly 1 part in 100 of the proton's mass, about 1%. The other 99% is not in the quarks at all. So where is it? The answer is energy, and the bridge between energy and weight is the most famous equation ever written. Albert Einstein showed that energy and mass are 2 faces of one thing, that energy has weight, and mass is a store of energy, joined by the speed of light squared as the exchange rate. Energy, bound up and held in place, weighs something, and the inside of the proton is packed with energy, the energy of the strong force, the churning gluon field, the ceaseless storm of the sea, the violent motion of the quarks racing inside their cage. All of that energy, by Einstein's rule, has mass. That mass is the proton's mass. Let this settle, because it overturns the oldest intuition we have about matter. You have always assumed, sensibly, that a thing weighs what its pieces weigh, that the heft of an object is the sum of the heft of its parts. A stone is heavy because it is made of heavy stuff. But the proton, which supplies almost all the weight of every atom in your body, does not work that way. Its weight is not the weight of its parts. Its weight is the energy of a force, trapped and held, read out as mass. The heft of your own hand is mostly the bound energy of the strong interaction, not the heft of any solid little pieces. This is what the title meant. What physicists found beneath the proton was not smaller, heavier balls that could explain its weight. They found the opposite. They found nearly massless quarks adrift in a field of pure energy, and that energy is the weight. The solidity of the world, the heft of stone and bone and water, rests not on solid stuff but on the caged energy of a force. The most ordinary thing about matter, that it weighs something, turns out to have an extraordinary source. It is worth being honest about the order of discovery here. The understanding that mass comes mostly from the strong field's energy did not arrive in one clean stroke. It grew as quantum chromodynamics matured through the 1970s and after, as physicists came to see that the energy of the gluon field, by Einstein's relation, had to dominate the proton's mass. The quark masses themselves come from a different source entirely, tied to another field that fills all of space, but those masses are tiny, and they are not the point. The point is that the proton weighs what it weighs because of bound energy, saying it is one thing. Proving it, calculating the proton's mass from the bare theory of quarks and gluons with no weight put in by hand, is another and far harder. That calculation took some of the largest computers ever built, and whether the answer would come out right was, for years, an open question. That is where we turn next. Saying the proton's mass comes from the energy of the strong force is one thing. Proving it is another, and for years it was a genuine question whether the theory could deliver the right number. Quantum chromodynamics is a precise set of rules for how quarks and gluons behave. In principle, those rules contain the proton's mass. You should be able to start with nothing but the theory, no measured weight slipped in by hand, and have the proton's mass come out. The trouble is that the strong force, fierce and self-tangled, defies the usual ways of calculating. For most of physics, you handle a hard problem by treating the force as a small nudge and adding up a series of ever smaller corrections. That works when the force is weak, the way electricity often is. It fails utterly for the strong force at the scale of the whole proton, because there the force is anything but small. The corrections do not shrink, they grow, and the neat series falls apart. The very strength that makes confinement also makes the proton impossible to handle with pen and paper. A different method was needed, one that did not lean on the force being gentle. The method that worked is called lattice quantum chromodynamics, and the idea behind it is to trade the smooth, continuous world for a grid. You imagine space and time not as a seamless flow, but as a fine mesh of points, a lattice, like the corners of a vast three-dimensional checkerboard. The quarks live on the points of the grid, the gluons live on the links between them, and the equations of the strong force become something a computer can grind through point by point. The grid is an approximation, but a controllable one. Make the spacing finer and finer, and the answer creeps toward the real, smooth world. The cost of this is staggering, and it is why the calculation waited so long. A useful lattice has so many points, and the strong force tangles them together so thoroughly that working out the proton's mass means tracking the interactions across the whole grid at once, an arithmetic so vast that no ordinary machine could finish it in any reasonable time. It took supercomputers, some of the most powerful ever built, running for months, racks of processors labouring in parallel on a single question. What does this theory say a proton should weigh? The answer came, and it is one of the quiet triumphs of modern physics. By the late 2000s, teams running these lattice calculations could compute the mass of the proton and of the neutron and the other particles from the bare theory alone. They put in the rules of quantum chromodynamics and the tiny masses of the quarks, nothing about the proton's own weight, and out came a number that matched the measured proton mass to within a few percent. The energy of the strong field, the churning gluons, the racing quarks, all of it, computed and added, gave the right weight. This was the proof. It confirmed, beyond a calculation done by hand, that the proton's mass really is the energy of the strong force made manifest. The theory was not just telling a nice story about where mass comes from, it could produce the number from first principles with no thumb on the scale. The agreement between the lattice answer and the laboratory measurement is one of the strongest pieces of evidence that quantum chromodynamics is the true theory of the proton's interior. So the question of weight is, in the deepest sense, answered. The proton is heavy because energy is heavy, and the strong force fills the proton with energy. But mass is only one of the things a proton has. It also has spin, a kind of built-in rotation, and the spin should be just as easy to account for from the quarks. The simple guess seemed obvious, and it was about to fail just as badly as the guess about mass. A proton spins, not in the way a top spins with parts whirling around a centre, but in a deeper built-in way that quantum particles carry as a basic property. Every proton has a fixed amount of this spin, the same for all of them, a quantity physicists write as 1/2 in the units they use. You do not have to set it turning, and you cannot stop it. The spin is simply part of what a proton is, as fixed as its charge. It is why a proton responds to a magnetic field, why the protons in your body can be made to line up and tip over inside a hospital scanner, and why magnetic resonance imaging works at all. Spin matters more than it might first seem, because it is woven through the structure of matter. The rule that two identical particles cannot share the same state, the rule that gives atoms their shells and the periodic table its shape, is a rule about particles with spin 1/2, and the proton is one of them. So the proton's half unit of spin is not a curiosity off to the side. It is part of the machinery that lets matter hold its form. Account for the proton's spin, and you understand something central about why the world is built the way it is. Now, the quarks inside the proton carry spin of their own. Each quark, like the proton, has a spin of 1/2, a built-in half unit, and spin, in the quantum world, can point in one of two directions along any axis you choose to measure, loosely up or down. So the obvious thing to do, once you know the proton is 3 quarks each carrying a half, is to add the quark spins and see if they make the proton's half. The bookkeeping is easy and it looks beautiful. Take the 2 up quarks and the down quark, point 2 of the quark spins up and 1 down, 2 halves up and 1 half down. The 2 opposing halves cancel, and you are left with a single half unit pointing up. 1/2, exactly the spin of the proton. Just as the quark charges added to the proton's charge, the quark spins seem to add to the proton's spin. The same 3 quarks, doing the same tidy arithmetic, explaining another of the proton's basic properties. It was clean, it was simple, and it fit. For a while, this was the settled picture, and it had the same satisfying feel as 2 up and 1 down giving the charge. The proton's spin was the spin of its 3 quarks, arranged so that 2 pointed one way and 1 the other. Every textbook could draw the little arrows. The quarks accounted for the charge, and now they accounted for the spin, and the proton seemed, in these respects at least, to be exactly the sum of its 3 valence pieces. The story hung together. It should have made anyone uneasy, given what had just happened with mass. There, the obvious guess, that the proton weighs what its quarks weigh, had failed by a factor of 100. The lesson of the mass was that the proton is not the simple sum of 3 quarks, that the gluons and the C and the bound energy do most of the work. Yet for spin, the simple 3 quark sum was still being trusted, the arrow still being drawn, as though the lesson stopped at weight. The trust was about to break, and it broke in an experiment. In the late 1980s, physicists set out to check the tidy spin arithmetic directly, to measure how much of the proton spin the quarks actually carried. They expected to confirm the picture. What the measurement found instead was so contrary to expectation that it earned a dramatic name, a crisis, and it sent the question of the proton spin wide open again. The experiment was done at the large laboratory called CERN, on the border between Switzerland and France, in 1987. A collaboration known by the initials EMC set out to measure, as directly as anyone could, how much of the proton spin was carried by the spins of its quarks. The method was to fire particles into protons whose spins had been carefully aligned, all pointing the same way, and to read off from the scattering how the quark spins inside were arranged. Everyone involved expected to confirm the textbook picture. The quark should carry essentially all of the proton's spin, the 2 up, 1 down arithmetic made plain in the data. The result was nothing of the kind. When the measurement was done and the numbers came in, the quarks were found to carry only a small fraction of the proton spin. Not all of it. Not most of it. Something like a quarter or less, with the rest unaccounted for. The tidy arithmetic, where 2 quarks spins up and 1 down summed neatly to the proton's half, simply did not describe the real proton. The quarks were spinning, but their spins did not add up to the spin of the whole. This landed hard enough to be named the spin crisis, and the word crisis was not for show. It meant that physicists did not understand where the proton spin came from. One of the most basic properties of one of the most common particles in the universe, a property exploited in every hospital scanner, and the obvious account of it was wrong by a wide margin. The proton has spin 1/2. Its quarks were supposed to supply that half. They supplied only a sliver, and the rest had gone missing. It is worth pausing on how unsettling this was, and how it rhymed with the lesson of mass. Once again, the simple sum of the 3 valence quarks had failed to give a basic property of the proton. With mass, the quark supplied about 1% and the strong field supplied the rest. Now with spin, the quark supplied only a fraction, and something else had to supply the rest. The pattern was becoming clear and a little humbling. The proton is not its three quarks. Again and again, the heart of the proton turns out to lie not in the quarks, but in everything else inside it, the gluons and the sea and the motion. The crisis did not mean the theory was broken. Quantum chromodynamics still stood. What it meant was that the proton spin was a far more complicated sum than anyone had drawn, with contributions that the simple picture had left out entirely. The missing spin had to be hiding somewhere inside the proton, in places the tidy arithmetic never counted. 3 candidates stood out at once. The gluons might carry spin of their own, the sea quarks might contribute, and the quarks and gluons might be orbiting inside the proton, carrying spin the way a planet circling the sun carries angular momentum, quite apart from any spin of its own. So the spin crisis turned a settled question back into an open one, and it sent physicists looking inside the proton again, this time for the source of its rotation. The measurement had been honest and the surprise was real, and the honest response was to admit that the proton's spin was not understood and to go find where it lived. That search has run for decades now, and it is still not finished. But the candidates can be laid out, and the progress that has been made is real, and that is where we go next. If the quarks carry only a fraction of the proton's spin, the rest has to come from somewhere inside, and physicists have spent decades chasing it down. The accounting is harder than it sounds, because the proton's spin must add up to exactly 1/2, no matter how the pieces share it, and the pieces are not easy to measure. But the candidates are clear. There are 3 places the missing spin can hide, and each has been hunted in its own way. The first place is the gluons. The gluons are not just passive glue. They carry spin of their own, each gluon a unit of the field with its own built-in rotation, and the proton holds a great many of them. If those gluon spins tend to line up with the protons, they add to the total. Measuring this is delicate work, because you cannot ask a gluon directly which way it spins. You infer it from how protons with aligned spins behave when smashed together at high energy, watching for small differences that betray the gluon's contribution. Experiments at the relativistic heavy ion collider on Long Island in New York spent years on exactly this, colliding spin-aligned protons to weigh the gluon's share. They found that the gluons do carry a real part of the proton's spin, a meaningful slice, though measured with wide uncertainty and not enough on its own to close the books. The second place is orbital motion. Picture the quarks and gluons not sitting still but circling inside the proton, sweeping around as they move. Anything that moves in a curved path carries angular momentum from that motion alone, quite apart from its own built-in spin, the way the Earth carries angular momentum from orbiting the Sun, on top of the spin that gives us day and night. The quarks and gluons inside the proton, swirling in their confined storm, can carry spin this way too, in their orbiting. This orbital piece may be large. It is also the hardest of all to measure, because it asks not just how the pieces spin, but how they move through the proton's interior, a far more detailed map than anyone has yet drawn. So the rough picture today is a sum with several terms, none of them the whole. The quark spins contribute their fraction, roughly 1/4 to 1/3. The gluon spins contribute another portion, real but uncertain, and the orbital motion of quarks and gluons is expected to make up much of the remainder, though it is the least pinned down. Add the measured and estimated pieces and they point toward the proton's 1/2. But the bars of uncertainty are still wide, and no one can yet write the full sum with confidence. The spin is not lost. It is spread across contributions that are genuinely hard to weigh. This is one of those places where honesty matters more than a clean ending. The proton's spin, more than 30 years after the crisis broke, is still not fully accounted for. Real progress has been made. The gluon contribution has been measured and found to matter. The orbital piece is being attacked with new experiments and new theory. The mystery has narrowed, but the simple question, where does the proton's spin come from, does not yet have a complete answer with every term nailed down. It remains, in the plain sense, open. That openness is not a failure. It is the live edge of the field, and it is one of the main reasons physicists are building a new machine designed in part to map the proton's spin in detail. Before we reach that machine, though, there is another basic property of the proton that turned out to hold its own surprise, gentler than the spin crisis but stubborn in its own way. The proton has a size, and even measuring how big it is led to a genuine puzzle. The proton has a size, but giving it one is harder than it sounds, because the proton has no hard surface. It is not a marble with a clean edge where the inside stops and the outside begins. It is that churning storm of quarks and gluons and C, and like any cloud, it fades at its margins rather than ending sharply. So when physicists speak of the proton's radius, they do not mean the edge of a ball. They mean something subtler, a measure of how the proton's charge is spread out, how far from the centre the charge typically reaches before thinning away. It is the size of a fuzzy thing, defined by where most of its substance lies, not by a wall. To picture the difficulty, think of trying to give a radius to a cloud, or to a city. A cloud has no skin. You can still sensibly say how big it is by where the mist grows thin, but the number depends on how you choose to measure the fading. The proton is the same. Its charge is densest at the centre and trails off outward, and the radius is a careful way of summarising that spread, a single number standing in for a soft, blurred distribution. That such a number can be measured at all, and measured precisely, is a real achievement. There are two classic ways to measure it, and for a long time they agreed. The first is to fire electrons at protons and watch how they scatter, much as in the deep inelastic experiments, but tuned to gently probe the spread of charge rather than to shatter the proton. The way the electrons deflect encodes how the charge is distributed, and from many such measurements you can extract the radius. The second way looks at hydrogen itself. In a hydrogen atom, a single electron orbits a single proton, and the electron's energy levels depend very slightly on the proton's size, because an electron that spends part of its time within the spread-out charge feels a subtly different pull. Measure those energy levels with great precision, and the proton's radius falls out. Both methods, the electron scattering and the hydrogen energy levels, gave the same answer for decades, a radius of a little under 1 femtometer, which is a millionth of a billionth of a meter, the unit that suits the proton's scale. The agreement was reassuring. Two completely different techniques, one smashing electrons off protons, and one reading the faint fingerprints of proton size in the colours of light hydrogen emits, converged on the same gentle number. The proton's size seemed as settled as its charge, and, until recently, its spin. It is worth holding the strangeness of the scale for a moment. A femtometer is so small that the numbers stop meaning anything by themselves, so try the comparison we used before. If the proton were swollen to the size of a pea, the whole hydrogen atom around it would span a sports stadium. The radius we're measuring is the size of that pea, read off to many decimal places by the faint shadow it casts on an electron's energy. To pin down such a thing at all is a marvel of careful work, so by the early 2000s the proton size looked like a closed question, a number agreed on by independent methods, sitting quietly in the textbooks. Then someone measured it a third way, using not an ordinary electron but a heavier cousin of the electron orbiting the proton in its place, and the new method returned a different number, smaller. Not by a trivial amount, but by enough to break the agreement and open a puzzle that took years to resolve. The proton size, of all things, became a genuine controversy. The new method swapped the electron for its heavier cousin. There is a particle called the muon, identical to the electron in every way that matters, except that it weighs about 200 times as much. You can build an atom with a muon in place of the electron, a muon orbiting a single proton, and physicists call it muonic hydrogen. The heavier muon orbits much closer to the proton than an ordinary electron does, diving deeper into the proton's charge, spending far more of its time inside the spread-out cloud. That makes it far more sensitive to the proton's size. The muon feels the proton's fuzziness more strongly, so reading its energy levels should give a sharper measure of the radius than ordinary hydrogen ever could. In 2010, a team measured the proton's radius this way, with monic hydrogen, and the answer came back wrong. Not wrong in itself, but wrong against everything before it. The muon gave a proton radius about 4% smaller than the long-agreed value from electrons and ordinary hydrogen. 4% sounds tiny, and on most scales it would be. But these measurements were so precise, their uncertainty so small, that a 4% gap was enormous, far larger than the error bars on either side. The two answers could not both be right, and nothing obvious explained the difference. This became known as the proton radius puzzle. The puzzle was sharp because it pitted precise measurements against each other with no easy escape. Either the electron measurements were subtly flawed, in a way no one had caught over decades, or the muon measurement was flawed, though it had been done with great care. Or most excitingly, the muon and the electron really did see different proton sizes, which would mean the muon was not quite the simple heavy electron everyone believed, and some new physics was lurking, some force or effect that touched muons differently. That last possibility set hearts racing, because a genuine difference between how muons and electrons feel, the proton would be a crack in the established picture of particle physics, a hint of something new. For several years the puzzle stood open and unresolved, and it is a good example of how science handles a clean contradiction. Nobody waved it away. Teams rechecked the electron scattering, reanalyzed old data, and built new experiments designed to measure the radius again with fresh methods, including new measurements of ordinary hydrogen aimed at the same precision as the muonic result. The community took the disagreement seriously as a real tension, neither dismissing the surprising muon number nor abandoning the trusted electron one. The honest position was that the proton size was for the moment uncertain, and the disagreement had to be tracked down rather than talked away. As the new measurements came in through the late 2010s, the tension began to ease. Several careful experiments with ordinary hydrogen and with electron scattering, redone with improved methods, started to land closer to the smaller value that the muon had found. The weight of evidence shifted toward the proton being slightly smaller than the old textbook figure, which suggested the earlier electron measurements had carried some subtle error rather than the muon revealing new physics. The exotic explanation, a new force singling out muons, faded as the simpler one strengthened. The puzzle is now largely, though not entirely, resolved in favour of the smaller radius, with the muon having essentially been right and the older value having been a little off. It is a quieter ending than a new force would have been, but it is a real one, and it shows the field correcting itself. It also leaves a lesson worth carrying. Even a number as basic as the proton size took heroic precision to settle, and the proton resisted easy measurement at every turn. Its fuzziness is not a flaw in our instruments. It is what the proton is, and that fuzziness deepens further when we look at the proton not gently, but with the full violence of the highest energies, where it stops looking like three quarks at all. To see the proton at its most extreme, you have to hit it as hard as physically possible, and for that there was a machine in Germany called Hera. At the laboratory known as DSY in Hamburg, physicists built a collider that did something no other machine has done since. It accelerated electrons in one ring and protons in another, in opposite directions, and smashed them into each other head-on at tremendous energy. It was, in effect, the Stanford experiment raised to a far higher power, electrons probing protons, but now with both beams moving near light speed and colliding with enormously more force, sharp enough to resolve the proton's interior in far finer detail than ever before. The harder you probe the proton, the more of its interior you resolve, and Hera probed very hard indeed. At Stanford, the electrons had energy enough to see the three valence quarks as point-like grit. At Hera's far higher energies, the picture that came back was different and stranger. The proton, seen this sharply, was not three quarks with a little extra. It was dominated by gluons, vast numbers of them, far outnumbering the quarks, filling the proton with the carriers of the strong force. The harder Hera looked, the more gluons it found. the proton appearing as an ever denser swarm of glue with the quarks almost lost inside it. This is one of the most striking and least told facts about the proton. In the simple story, the proton is 3 quarks, and that is where most accounts stop. But probe it at high energy, and the quarks are the minority. The proton, examined closely, is mostly gluons, a roiling crowd of force carriers, with the quarks as a thin population swimming through them. The thing we call a particle of matter is, looked at sharply enough, overwhelmingly a knot of the strong force's own carriers. The glue is not a supporting detail. At high energy, it is the main thing there. Why does looking harder reveal more gluons? Because the gluons are forever splitting and multiplying. Recall that a gluon can split into a quark-antiquark pair and into more gluons in the endless churning of the sea. A sharper probe, with its shorter wavelength, catches these brief splittings in finer detail, resolving one gluon into the several pieces it has momentarily become. So the count of pieces you see depends on how hard you look, rising as the probe sharpens. There is no single true number of gluons in the proton. There is a number for each scale of probing, and that number climbs without obvious limit as the energy rises. HERA ran from the early 1990s into the late 2000s, and its careful mapping of how quarks and gluons share the proton's interior became one of the foundations for understanding what happens in other high-energy collisions. When protons are smashed together in the largest collider of all, the interior revealed by HERA is the starting point for predicting what will come out. The German machine drew the most detailed map yet of the proton's insides at high energy, and that map is gluon country. So the proton's appearance is not fixed. Gently probed, it is a fuzzy cloud of charge with a soft radius. Probed at Stanford's energies, it is 3-point-like quarks. Probed at HERA's far higher energies, it is a dense swarm of gluons with quarks scattered through. The same proton, 3 different faces, depending entirely on how hard you look. That dependence is not a confusion to be cleared up. It is a real and central feature of the proton, and physicists have a precise way of describing it, a way of writing down how the proton's contents shift with the sharpness of the probe. That description is where we turn next. The proton looks different depending on how hard you probe it, and that is not vagueness. It is something physicists describe with precision through a tool called the Proton distribution. The idea is to stop asking for a single snapshot of the proton's contents and instead ask a sharper question. At a given strength of probing, what is the chance of striking a piece carrying a given share of the proton's total momentum? The answer to that question, mapped out across all the possible shares, is the Proton distribution, and it is how the proton's interior is actually written down in modern physics. Start with momentum, because that is what gets shared. The proton, moving along, carries a total momentum, and every piece inside it, each quark, each antiquark, each gluon, carries some fraction of that total. A piece might carry a large share, or a tiny sliver, and the Proton distribution tells you how likely each is. It is like asking, of all the people in a crowd carrying a fixed total of money among them, how many hold a large amount and how many hold only small change? The distribution is the full answer, the spread of shares across the whole population inside the proton. What the distributions reveal is that the sharing is lopsided and shifting. At lower probing energies, much of the momentum sits with the 3 valence quarks, each carrying a respectable share. Probe harder, and the picture changes. The valence quarks give up the spotlight, their momentum spread among an ever-growing crowd of gluons and C-quarks, each carrying a smaller and smaller sliver. The harder you look, the more the proton's momentum is divided among many low-share gluons, which is the same gluon dominance HERA found, now written precisely as a distribution that shifts towards small shares as the energy climbs. This is the formal heart of the idea that the proton looks different depending on how you look. The Proton distributions are not fixed numbers. They change with the strength of the probe, and the way they change is itself predicted by the theory of the strong force. through equations that tell you how the distributions evolve as you sharpen your view. So while there is no single fixed inventory of the proton, there is something better. There is a precise rule for how the inventory shifts from one scale to the next, a rule confirmed against experiment again and again. The proton's shifting appearance is lawful, not arbitrary. These distributions are not an abstraction off in theory. They are essential, practical tools, the working description of the proton that physicists reach for whenever protons collide. At the Large Hadron Collider, the giant machine near Geneva where protons smash together at the highest energies ever reached, every prediction about what should come out of a collision starts with the Proton distributions of the two protons. To know the odds of producing a particular particle, you need to know how the colliding protons share their momentum among quarks and gluons, because it is really those pieces that collide. The discovery of the Higgs boson, the careful tests of the Standard Model, all of it rests on knowing the proton's interior through these distributions. So the answer to how the proton looks has become wonderfully precise, even though it refuses to be a single picture. The proton is described not by one snapshot but by a family of distributions, one for each scale of probing, tied together by the equations of the strong force. Ask gently, and you see valence quarks. Ask hard, and you see a sea of gluons. The Proton distributions hold all those answers at once and tell you how to move between them. And tucked inside these distributions, at the edge of what can be measured, sits a subtle effect that most tellings of the proton story leave out entirely, a hint that the proton may hold a flicker of something heavier than anyone expected. Most tellings of the proton story stop at the up and down quarks, with the sea treated as a vague background. But there is a subtler feature, often left out, that is worth bringing into the light, because it shows how rich the proton's interior really is. It concerns a heavier kind of quark called charm, and the question of whether the proton holds a little of it not just as a fleeting flicker of the sea, but as a genuine, lasting part of what it is. First, the charm quark itself. Beyond the up and down quarks that build ordinary matter, nature has heavier quarks, and charm is one of them, considerably more massive than the up or down, even heavier than the proton in a sense, when you account for how mass works at these scales. Because it is so heavy, charm is not part of the proton's defining recipe. The proton is 2 up and 1 down, and charm has no place in that list. Yet the sea inside the proton, the churning broth of flickering pairs, can briefly conjure charm quarks too, when the gluon field musters enough energy to make a charm-anti-charm pair for an instant before it vanishes. That much is ordinary sea, and no surprise. The subtle claim goes further. It is the idea that the proton carries some charm not merely as these brief flickers, but as a more permanent built-in component, present in the proton's very structure rather than conjured fresh each instant. This is called intrinsic charm, and the distinction matters. Flickering sea charm comes and goes with the probing. Intrinsic charm would be there as part of the proton's makeup, a small but real charm content woven into the bound state itself, carrying its own share of the proton's momentum in a way the simple sea picture would not predict. The idea of intrinsic charm was proposed decades ago, and argued over for a long time, because it was hard to test and easy to confuse with the ordinary sea. Distinguishing a permanent charm component from the flickering kind takes very careful measurement of how the proton's contents are distributed, especially among the pieces carrying larger shares of momentum, where intrinsic charm should leave a particular mark. For years the evidence was suggestive but inconclusive, and the question sat unresolved, a long-running argument at the edge of the field. In recent years the evidence has firmed up. A careful analysis of a vast body of collision data, examining the proton's Proton distributions with great statistical care, reported the first strong signs that the proton does carry intrinsic charm, a small genuine charm content beyond what the flickering sea would give. The signal was modest, the charm carrying only a tiny fraction of the proton's momentum, but it was there, in the place the theory of intrinsic charm had long predicted it should be. The proton, it seems, is even more crowded than the standard story says, holding a faint permanent trace of a heavy quark that has no business being in the simple recipe at all. This is the angle the common videos leave out, and it is worth carrying for what it reveals about the proton's nature. The proton is not a clean assembly of 3 light quarks. It is a deep, layered object whose contents reach beyond its own defining pieces, down into heavier quarks that flicker and in part abide. Each time physicists look more carefully, the proton turns out to hold more than expected, and every layer of that richness, the gluons, the sea, the intrinsic charm, points back to the same source. It all comes from the strong force, the one interaction that fills the proton and, as we are now ready to say plainly, makes the proton what it is. Step back now and see the whole shape of what we have found, because a single idea runs through all of it. We asked what the proton is made of, expecting an answer in terms of parts, smaller pieces that would explain the proton the way bricks explain a wall. What we found instead is that the proton's deepest properties do not come from its parts at all. They come from the force that binds the parts. The proton at bottom is less a collection of objects than a knot of the strong interaction, and nearly everything about it flows from that. Look at what we have seen, property by property. The proton's mass, the heft you feel in every object, is almost entirely the energy of the strong field, not the weight of the quarks, which supply about 1%. The proton's spin, its built-in rotation, is not the simple sum of 3 quark spins, but a complicated total spread across gluon spins and the orbital motion of everything inside, with the quarks carrying only a fraction. Even the proton's size, the soft radius of its charge, is set by how far the binding lets the charge spread before the strong force reins it in. Mass, spin, size. Not one of them is the property of the parts. Each is a property of the force. This is the real answer the title promised, and it inverts the expectation we began with. We started with a marble, a tiny solid ball, and assumed that looking inside would reveal smaller solid pieces that added up to the whole. The smaller pieces are there, the quarks, real and confirmed. But they are nearly massless, they carry little of the spin, and they cannot even be pulled out. What gives the proton its weight, its rotation, its size, its very stability, is the strong force itself, made tangible. The proton is what a force looks like when it ties itself into a stable, lasting knot. Sit with how strange and beautiful that is. You're made of atoms, and almost all the weight of those atoms is in their protons and neutrons, and almost all the weight of a proton is not stuff but bound energy. The strong force held in a standing pattern, the solidity of your body, the heft of a stone, the mass of a star traces back not to some final hard substance, but to the energy of an interaction, caged and persistent. Matter at its root is mostly force. The world feels solid because the strong force makes it so, not because there are tiny solid balls underneath holding everything up. And the quarks, for all that they cannot supply the mass or the spin, are still essential, because they are what the force binds. Without the quarks, there is nothing for the strong force to knot around, no valence pieces to fix the charge and the identity, no seed for the storm. The proton is quarks and force together, inseparable. The quarks giving the force something to hold, and the force giving the quarks their weight and their permanence. You cannot have one without the other, and you cannot pull them apart, which is confinement stated in plain words. So the proton turns out to be a far more profound object than the smallest brick of matter. It is a demonstration, sitting in every atom of you, that the deepest things about matter come from interaction rather than substance. The lesson hidden beneath the proton is that the world is built less from things than from the forces between things, with the forces carrying the weight in the most literal possible sense. That is what physicists found when they looked inside, and it does change everything about how to picture what you are made of. This profound object is not locked away in laboratories. It is the most ordinary thing in the world, and it does ordinary vital work. Before we ask whether the proton lasts forever, it is worth seeing the proton at its day job, holding up matter and lighting the sun. For all its hidden depth, the proton is the most ordinary thing in the world, and it spends its existence doing quiet, essential work. start with the simplest case, the one we began with. A single proton, alone, with one electron circling it, is an atom of hydrogen, the lightest and most abundant element in the universe. Most of the ordinary matter in existence, the stuff of stars and clouds of gas spanning the galaxies, is hydrogen, which is to say it is single protons with their electrons. When you look at the night sky, most of the visible matter out there is, at its core, lone protons. The proton is not exotic, it is the common substance of the cosmos. Bring hydrogen together with oxygen, and you get water, 2 protons worth of hydrogen bound to an oxygen atom in every molecule, and water is where the proton touches your life most directly. Every glass you drink is built on protons, the hydrogen nuclei threaded through it. Your body is mostly water, which means your body is, in large part, a careful arrangement of protons and the electrons and heavier nuclei among them. The heft of you, as we have seen, is mostly the bound energy of the strong force inside those protons. You are, in a real sense, walking proton structure, the strong interaction made into something that can wonder about itself. But the proton's grandest job is in the stars, and it is the reason the sun shines. Deep in the sun's core, under crushing pressure and tremendous heat, protons are pressed so close and moving so fast that they begin to fuse. 2 protons, then more, join together through a chain of steps into the nucleus of helium, the next element up. This is proton-proton fusion, the process that powers the sun and most stars like it, and it is worth seeing how it depends on everything we have built. The protons must overcome their fierce electric repulsion, both being positive, to get close enough for another force to take over and bind them. Here a quiet detail deserves attention, the kind the common tellings skip. When 2 protons fuse, one of them must turn into a neutron for the helium nucleus to form, and that conversion is not done by the strong force at all. It is done by a different, far feebler force called the weak force, the same force behind certain kinds of radioactivity. The weak force is so slow to act that 2 protons, even jammed together in the sun's core, must wait an enormous time on average before one converts and the fusion proceeds. This slowness is why the sun burns gently over billions of years instead of exploding. The proton's reluctance to fuse, set by the weak force, is what gives the sun its long, steady life. That long, steady burn is what made you possible. The sun has shone for some 4.5 billion years and will shine for billions more, all on the slow fusion of protons in its core, releasing the energy by Einstein's relation as a tiny bit of mass is lost in each joining. Every ray of sunlight that warms your face, every photon that grew the plants at the base of all our food, began as protons fusing deep in the sun. The proton is not just the brick of matter, it is the fuel of the star that gives us light and life, working through the patient, plodding weak force to keep the fire low and lasting. So the proton holds up the everyday world and powers the sky. It is the heart of hydrogen, the substance of water, the fuel of the sun. And through all of this we have quietly assumed one thing about it, that it lasts. The proton seems permanent, never seen to die. But is it truly forever? Or does even the proton, given enough time, eventually come apart? That question turns out to reach to the deepest theories we have. We have assumed all along that the proton lasts forever. Nothing in this story has shown a proton dying, and in all of human experience none ever has. The proton seems to be the one truly permanent piece of matter, stable across the entire age of the universe. But seeming permanent and being permanent are not the same, and some of our deepest theories suggest that even the proton might, given almost unimaginable time, eventually come apart. Whether it does is one of the great open questions, and the search for the answer is a story of patience on a staggering scale. The reason to suspect the proton might decay comes from the dream of unification. The forces of nature look separate at the energies we can reach. The strong force, the weak force, electromagnetism, each with its own character. But there are theories, called grand unified theories, that propose these forces are really facets of a single deeper force, distinct only because the universe has cooled. At enormous energies far beyond any machine, the three would merge into one. These theories are elegant and have drawn physicists for decades, and they make a startling prediction as a side effect. If the forces unify, then the rules that keep the proton stable are not absolute, and the proton must very rarely decay. The reason is that unification tends to blur the line between quarks and the lighter particles like electrons. In our world, that line is firm, and it is part of why the proton is stable, because there is nothing lighter for its quarks to turn into while obeying all the rules. But if quarks and lighter particles are deeply related as unification suggests, then a proton's quarks could, on rare occasion, convert, and the proton could fall apart into lighter pieces, perhaps a lighter particle and a burst of energy. The proton would not be eternal after all. It would simply be extraordinarily long-lived, decaying so rarely that we have never happened to see it. How rarely? The theories predict a proton lifetime so vast it defeats comparison. The universe itself is about 14 billion years old. The predicted average lifetime of a proton is something like 1 billion times longer than that, a number with more than 30 zeros in years. No single proton is likely to decay in any time we could watch. But here physicists use a clever trick. If you cannot wait for one proton through its impossible lifetime, gather an enormous number of them together and watch them all at once. With enough protons in view, the rare decay should happen to one of them now and then, even within a human span of watching. That is exactly what the great proton decay experiments do. In Japan, deep under a mountain, sits a detector called Super Kamiokande, an enormous tank holding 50,000 tons of ultra-pure water, which is to say an immense number of protons, watched by thousands of sensitive light detectors lining its walls. It sits deep underground to shield it from the constant rain of other particles that would swamp the signal. The experiment waits, year after year, for a single proton among that vast number to decay and produce the telltale flash its sensors are tuned to catch. It is one of the most patient watches in all of science, and so far the watch has caught nothing. No proton decay has ever been observed in Super Kamiokande or in the experiments before it. This does not prove the proton is eternal, but it pushes the minimum possible lifetime to staggering lengths, long enough to rule out some of the simpler unified theories that predicted faster decay. The proton, if it dies at all, dies more rarely than the first guesses supposed. The question stays open, the watch continues, and what hangs on the answer is nothing less than the long-term fate of all matter. So the proton may be eternal, or it may merely be almost eternal, and the difference, small as it sounds, decides the fate of everything. Take in the timescales first, because they are beyond ordinary grasp. The longest lifetime the experiments now allow for the proton is something like 10,000 billion years, a number so large that the present age of the universe, 14 billion years, is less than a rounding error against it. If the proton does decay, it does so on a clock that makes the entire history of stars and galaxies so far look like the first instant of a far longer day. Try to feel that span by stretching it out. Imagine the universe aging far past anything we know. The stars burn through their fuel and die, the last of them flickering out after trillions of years, leaving cold, dark remnants. Galaxies drift apart and grow dark. For an almost endless stretch after that, the cold remnants of stars, the burned-out cinders and the dead husks would drift through an ever emptier cosmos, made of the same protons that fill you now. If the proton is truly stable, those cinders endure essentially forever, matter persisting in the dark without end. The universe would grow cold and quiet but never quite lose its substance. But if the proton decays, even on that impossibly slow clock, the story ends differently. Given enough time, far past the death of the last star, the protons themselves would begin to crumble. The cold remnants would slowly evaporate from within as their protons converted one by unimaginably rare one, into lighter particles and radiation. Over a span so long it dwarfs everything that came before, ordinary matter would dissolve, the cinders would fade, the structure would unwind, and the universe would drift toward a thin haze of light particles and radiation, with the solid matter all gone. Even the dead husks of stars would not last. Nothing built of protons would remain. This is the deep stake hidden in those underground tanks of water. The proton decay experiments are not just testing an abstract theory of unified forces. They're asking whether matter is permanent, whether the stuff you're made of has a true end written into it, or whether it can, in principle, persist without limit. The answer touches the longest question there is, the final fate of everything material, and it is being chased by watching ordinary water for a flash that may never come, or may come once and change the picture entirely. It is worth holding the honesty of this. We do not know whether the proton decays. We know only that if it does so more rarely than a vast lower bound, and that the simplest theories predicting quicker decay have been ruled out by the silence of the detectors. The proton might be perfectly stable, matter's one truly eternal piece, or it might carry a slow seed of its own undoing, set by forces that unify only at energies we will never reach. Both remain possible, and the experiments narrow the question without yet closing it. Either way, the timescales humble us in a useful way. Against the proton's lifetime, every human concern, every civilization, the whole run of life on Earth, occupies a sliver so thin as to vanish. The proton you carry has existed since the first minutes after the universe began, nearly 14 billion years ago, and will outlast the Sun, the Earth, and very likely the last star. You're made of some of the oldest and most durable objects in existence, briefly borrowed and arranged into a person who can ask how long they last. That is a strange and moving thing to be. To narrow these questions further, the ones about the proton's spin, its decay, its detailed interior, physicists are building a new machine designed to look inside the proton more sharply than anything before it. That machine is where we turn now. To answer what is still unknown about the proton, physicists are building a new machine, and it is designed for exactly this object. It is called the Electron-Ion Collider, planned to be built at Brookhaven National Laboratory on Long Island in New York over the coming years. Its purpose is singular in a way most big machines are not. It is not built mainly to discover new particles or to chase higher energies for their own sake. It is built to map the inside of the proton and of larger nuclei in more detail than has ever been possible, to turn the blurred and partial pictures we have into something far sharper. The design follows directly from everything we have learned about how to see inside a proton. It will collide electrons, the clean point-like probes that revealed the quarks at Stanford, against protons and heavier nuclei, the way Hera did in Germany, but with crucial new powers. It will be able to control the spin of both the electrons and the protons, aligning them precisely, which is what you need to attack the spin question directly, and it will collide them across a wide range of energies, so the proton can be probed gently and harshly, and at many scales between, tracing how its contents shift as the sharpness of the view changes. What the Electron-Ion Collider promises is something genuinely new, a map of the proton in 3 dimensions. Until now, the Proton distributions have told us how the proton's momentum is shared among its pieces, a kind of one-dimensional accounting of who carries what fraction. The new machine aims to go further, to chart not just how much momentum each piece carries, but where the pieces sit inside the proton and how they move, building up a 3-dimensional picture of the proton's interior, the positions and motions of the quarks and gluons within the storm. It would be the closest thing yet to a true image of what a proton looks like inside. That 3-dimensional map is aimed squarely at the open questions we have met. On spin, by colliding spin-aligned electrons and protons across many energies, the collider should pin down how much of the proton's spin comes from the gluons and, hardest of all, how much comes from the orbital motion of the pieces inside, the term that has resisted measurement most stubbornly. It is designed to finally close, or come close to closing, the accounting that the spin crisis opened nearly 40 years ago. The missing spin should have far fewer places to hide once the new map is drawn. The machine reaches at the deepest puzzle too, the nature of confinement and the gluon field itself. By probing how gluons crowd and behave inside protons and inside large nuclei, where their density climbs highest, the collider may reveal new things about how the strong force packs itself into matter, perhaps even a predicted state where the gluons grow so dense they saturate, crowding as tightly as they can. Studying the glue at this density gets at the heart of how the strong force builds a proton, the very mechanism behind mass and confinement that we can describe but not yet fully derive. The Electron-Ion Collider is a long-term project, years in the building, and it represents a deliberate choice by the physics community to turn its most advanced tools back onto the proton itself, the object we thought we understood longest ago. That choice is a kind of admission, an honest one. After more than a century, the proton still holds questions worth a machine of this scale. We know it is quarks and gluons bound by the strong force, and we know that force gives it mass and size and most of its spin. But the full, detailed picture, the three-dimensional truth of the proton's interior, is not yet in hand. The new collider is built to go and get it, and to settle what we still cannot. It is worth being plain about how much remains unknown, because the proton, for all we have learned, still guards real mysteries, and honesty about them is part of understanding it. We have not tied a neat bow on this object. We have a powerful, well-tested theory of its interior, quantum chromodynamics, that has passed every experimental test put to it. And yet several of the deepest questions about the proton are genuinely open, not because the theory is wrong, but because it is so hard to solve and so hard to probe. Begin with confinement, the rule that no quark can ever come out alone. We have described it, pictured it as the elastic band that snaps into new pairs, traced it to the gluons clinging to themselves. But describing confinement is not the same as proving it. No one has yet shown, with full mathematical rigour, that the equations of the strong force actually forbid a free quark, that confinement truly follows from the theory rather than merely fitting it. It is observed in every experiment and reproduced in the great lattice computations, but a clean proof from first principles does not exist. We are confident confinement is real, and confident the theory contains it, and we still cannot derive it cleanly. This open problem is serious enough to carry a prize. Among the 7 Millennium Prize problems, a set of the hardest unsolved questions in mathematics, each with $1 million award, one asks for exactly this. It calls for a rigorous proof that the theory of the strong force, the kind that governs the proton, has what is called a mass gap, a property closely tied to confinement and to why the force is short-ranged and its bound states have the masses they do. The problem has stood unsolved since the prizes were announced at the turn of the millennium. The proton's binding, the everyday fact that quarks stay locked inside it, sits among the great unsolved problems of mathematics, unproven at the deepest level. The spin, too, remains unsettled, as we have seen. Nearly 40 years after the spin crisis, the full accounting of where the proton spin comes from is not closed. The quark spins supply a fraction, the gluon spins supply a measured but uncertain piece, and the orbital motion is expected to make up much of the rest but has not been pinned down. The sum points toward the proton's one half, but with uncertainty still too wide to call the books balanced. We know the spin is there, we know roughly how it is shared, and we cannot yet write every term with confidence, and there are subtler open threads, the precise three-dimensional structure of the proton, the exact size and behaviour of its gluon field at the highest densities, the firm confirmation and full understanding of its intrinsic charm, even the last residue of the radius puzzle. None of these is a crisis for the theory. All of them are places where the proton still has more to tell us, where the detailed truth outruns what we have measured or solved. The proton is not a closed book. It is a well-understood object with a stubborn, fascinating core of unanswered questions. This is the honest state of things, and it is a good place to be. We understand the proton well enough to know what we do not understand, which is its own kind of knowledge. The grand picture is secure. The proton is quarks and gluons, bound by the strong force, which supplies its mass and most of its other properties. The open questions are sharp and specific, the kind that drive new machines and new mathematics. After more than a century of looking, the smallest brick of matter still leads physics toward its frontier, which is perhaps the truest sign of how deep it goes. So let us gather all of it together and return at the end to where we began, with the weight of your own hand and the simple question of what it is made of. Hold up your hand again, the way you did at the very beginning, and feel its weight. We can answer now in plain words the question we started with. What is that weight, and what is your hand made of, all the way down? Your hand is mostly water and the stuff built from it, and that stuff is atoms, and almost all the weight of those atoms lives in their protons and neutrons. So when you feel the heft of your own hand, you are feeling protons, by the countless billion, the same particles we have spent this whole time taking apart. And what is each of those protons? Not a tiny solid ball as everyone first thought. It is 3 quarks, 2 up and 1 down, that set its charge and its name, swimming in a churning storm of gluons and a sea of flickering pairs, all bound together by the strong force. The quarks themselves weigh almost nothing, about 1% of the whole. The rest of the proton's weight, 99 parts in 100, is the energy of the strong force, caged and held, turned into mass by the deepest exchange rate in nature, energy into weight. The heft of your hand is almost entirely bound energy. It is force, made solid. That is the answer the title promised, and it does change the picture of what you are. You're not at bottom made of a little solid pieces stacked up. You're made of force tied into stable knots, of energy held in standing patterns by an interaction so strong its pieces can never be pulled free. The solidity you feel, the weight in your hand, the firmness of the table it might rest on, all of it traces back not to some final hard substance, but to the trapped energy of the strong force. Matter, looked at closely enough, is mostly not stuff. It is interaction, persistent and bound. Widen out from your hand now, because the same truth scales all the way up. The mountains, the oceans, the Earth itself, the sun and every star are built of protons and neutrons, and so their weight too is mostly bound energy of the strong force. The sun shines by fusing protons, the patient slow fire that gives us light and made life possible. The visible universe, the vast clouds of hydrogen drifting between the stars, is mostly lone protons, the same object you hold in every drop of water. From your hand to the farthest galaxy, the substance of the material world is this one knot of force, repeated beyond counting. And these knots are old, almost beyond meaning. The protons in your hand formed in the first minutes after the universe began, nearly 14 billion years ago, and they may well outlast the sun and the last star, persisting for a span that makes all of cosmic history so far look like an opening instant. We do not even know for certain that they ever truly die. You are, for this brief while, a particular arrangement of some of the oldest and most durable objects in existence, borrowed from the universe and gathered into someone who can look down at their own hand and wonder what it is. That is the quiet astonishment underneath the ordinary. The proton seemed the smallest, simplest, most settled brick of matter, and when physicists finally looked inside, they found not smaller bricks but a storm of force that supplies nearly all of what matter is. Its weight, its stability, its very persistence through time. The thing beneath the proton was never a smaller solid piece. It was the strong force itself, and that is what holds you together and gives you your weight. So the next time you feel the heft of something in your hand, you can know what you're really feeling. You're feeling the energy of a force tied into knots 14 billion years old, briefly arranged into you.